So let's have a look at one of McCain's little trick questions. I hate these. So 2-9. This one's a little trickier than you think. So you got a sealed container. Uh, volume equals 1 cubic foot. And mass is 40 pounds of isopentane, which has another name, which I'll find out here in a minute. So isopentane, 40 pounds, and most importantly, temperature equals 150 degrees Fahrenheit. And we want to calculate the volume of the liquid in the container. So this is total volume. We want to calculate the volume of liquid because you could potentially have liquid or you could have gas. But to have that, you would have to be on the vapor pressure at this temperature. So step one, we could go look at the chart and we could see what pressure that's at. But that's not so important right now. I think more importantly, to be able to solve this, you would have to use a couple of equations. So here's one of them. The mass is equal to the volume of the liquid times the density of the liquid plus the volume of the gas times density of the gas, and that's going to equal to our 40 pounds, right? We've already got that up here. The other thing is the volumes have to add up. So volume of liquid, volume of liquid plus volume of gas has got to equal 1 cubic foot. We can rearrange that and make the volume of liquid, which is what we're looking for, is equal to 1 cubic foot minus the volume of gas. So we need to solve these equations. So we're going to need to know these densities of liquid and gas of the isopentane at temperature. So there's the method that McCain would recommend actually ends up being quite comical, or the way it would supposed to be doing it in the book is here, if you see over here your fluid densities, and you're supposed to, let's zoom in here. Can you read isopentane anywhere on that chart? I certainly can't. It's in here somewhere. Here's isobutane. Here it is, isopentane. It's kind of crammed in there. Oh, geez. So I do have the original source for that here. Not that this helps you anymore, but I can see this and read it a little better because it's cleaner. So here's isopentane's line. You'd follow it around. So if I got a ruler and I came to the 150 Fahrenheit mark here on the, and then I see where it crossed the line. I got some density that's like really tiny. This is the gas density because this is the density temperature curve. So I got some little tiny density, and up here I've got some higher density for the liquid. So this is the liquid side of the curve. This is the gas side of the curve. I do not like using this method because it's not very accurate. So let's throw these out of the way for a minute. Let's come back to how I would choose to solve this problem. Let me drag something on the screen over here, and let's focus on this for a minute. Let's get this out of the way. So if you look, this is chemistry web book from NIST. Let me zoom in a little bit. So they have this thermophysical property of fluids database, and if you come on it, this is what we want. We want to find some properties. We want to find it in Fahrenheit, PSI, pounds per cubic foot. We'll choose those for right now. And then let's find our isopentane. If you go looking through here, you will not find it. That is because 2-methylbutane is the same thing as isobutane. It's just the same thing, different name. You just need to know that for this problem. I wouldn't expect you to memorize that. So let's press to continue. So inner temperatures. So we want to know 150 Fahrenheit. This is asked for in Fahrenheit. That's what we chose. And then pressures. I'm going to choose 0 to 100 because I know that the pressure that we're looking at, the vapor pressure, is in between there. I could have shown you that if I wanted to. Here, let's look at that for a second. Drag this out of the way. If we come back to the book over here and find, where's the Cox charts? Cox charts. Let me find you. Cox charts. Let me zoom out here a second so I can find it. Another number. Ah, here they are. So the Cox chart might be hard to see also. So here's, where's isopentane? We may need to rotate this so that you can see it. Let's rotate it so we can see it a little better. So see, this is equally bad. Isopentane, here's the curve. So if we come out to 150, let's see, it's hard to draw a line out. Anyway, here's the 150. We come up to where it hits roughly the isopentane. You can see 2-methylbutane. We're somewhere around 40 something, 50 somewhere right here. That's not very accurate. So I know it's somewhere between 0 and 100. So I can put that here. So 0 to 100 is what I'm putting in here. And increment, let's do increments of 1/10 of a psi. Now let's crank us out a data table. Here we go. Here's the plot of it. So down here we've got our vapor pressure line. And then right here, it makes a jump. We go to liquid. You can see by the colors up here. So we can look, our vapor pressure, we want to take that down. Our vapor pressure is equal to 46.035 if you're a really accurate person. And let's go ahead and write that density down. So density of the gas is equal to 0.56221 pounds per cubic feet. And then the density of our liquid up here is 46.035 pounds per cubic feet. So there's something very interesting going on here. Let's see, we've got our calculation. We got everything we need for our calculation, I believe now. Oh, I'm sorry. This is where I just made a mistake. That's the pressure. I really need the density 3675. So now this is the interesting part. Up here, I just told you the mass is 40 pounds and it's in 1 cubic foot. So that density would be 40 pounds per cubic foot. 40 is greater than 35, hence there is no gas in there. So the volume of the liquid is actually equal to the volume total, which is 1 cubic foot for this case. This is actually a trick question. If you go through and solve these equations out, you would get a negative value for V sub G, and you can't have a negative volume of something. But that's how this problem works. So here's your answer. It's 1 cubic foot of liquid isopentane in this question.